All right, welcome back to another lecture. I'm excited to dig into Chapter 3. In this unit, we're going to be exploring inference. So we're kind of going to pick up where we left off at the end of Chapter 1, and we're going to use some of the tools that we developed in Chapter 2 in order to extrapolate and say what we can conclude from what we observe in the data. And just to kind of motivate the discussion here a little bit, I want to begin by looking at a few examples. So this first one says, a random sample of 300 children were given Medco's new antibiotic, and 2.3% of them experienced a headache after taking the medication. A researcher for the Food and Drug Administration wishes to know if we conclude that more than 2% of children taking this new antibiotic experience headache as a side effect. Is there enough of a difference here to make that claim? So, all right, so there's kind of a lot of words there. You could pause the video and kind of read through the scenario again to make sure it makes sense to you. But the situation is this. We want to know if more than 2% of children who take this medication will experience a headache as a side effect. So we went out and we sampled 300 children and found that 2.3% of them experienced a headache as a side effect. And now, at first glance, you might say, well, yeah, 2.3% is more than 2%. But you know about sampling distributions, and you know that sometimes just by random chance, you might have a sample proportion that's a little bit larger than the population proportion, right? So it could just be the case that we just so happened to get a sample of 300 children who were a little bit more prone to headaches than children typically tend to be. And so, can this evidence really be used to say that this new antibiotic causes headaches more than 2% of the time? Or is this 2.3% just kind of like a fluke? Certainly, the difference between 2% and 2.3% is only a 0.3% difference. It's just not that much different. So I would be inclined to say that, no, there's probably not enough of a difference here for us to say that the antibiotic causes headaches or causes headaches more than 2% of the time. But it's hard to know, right? Like, it's hard to know if that's good enough evidence or not. Here's another example, right? So number 2 says, according to QSR magazine, Chick-fil-A fills their drive-thru orders with 96.4% accuracy. A curious fast food fanatic wonders if the accuracy is different at her local Chick-fil-A. So she collects information from a store manager about the drive-thru accuracy of the local Chick-fil-A. In 350 orders, it was found that 93% were accurate. Is this a large enough difference, right? To say that the accuracy rate at the local Chick-fil-A is different from the national rate. Well, at the national level, the accuracy rate is 96.4%. And in our sample of 350 orders, the accuracy rate was only 93%. So that's like a 3.4% difference. Is that enough of a difference for us to say that our local Chick-fil-A is not as accurate? Well, or is it possible that that's just due to random chance, right? Is it possible that we just so happened to get a sample of 350 orders that, were a little bit less accurate, but maybe if we went out and collected a different sample of 350 orders, we would get something more than 96.4%, right? So what's going on here? Can we say officially, that our Chick-fil-A is less accurate? Again, not easy to answer that question, okay? Let me give you one last example. A recent poll found that 83% of people say they like unicorn giggles. A tired parent believes that percentage would decrease if people were first required to watch an episode of My Little Pony before saying whether they like unicorn giggles, right? So if you make them watch this annoying show, maybe they're less likely to say that they like it, right? 150 participants were randomly selected and made to watch an episode of the show, and afterward, 77.3% of participants reported liking unicorn giggles. Is there enough of a difference? Well, this is the biggest difference of all the ones that we've considered so far, right? 83% versus 77.3%. That's almost a 6% difference. But again, it could be that this decrease was just due to random chance. Maybe we just so happened to get 150 people who were just naturally less enthusiastic about unicorn goggles, and it had nothing to do, with having watched the show first. So the moral of this story is that, man, it would be really nice to have a mathematically rigorous way to decide when we have sufficient evidence to support our claims. And that's exactly what hypothesis testing is, right? Hypothesis testing is the mathematically rigorous tool that we use to decide if we have enough evidence to support our claims. So what we're going to do in this section is we're going to build up the steps for the hypothesis testing procedure one step at a time. And while we're at it, we're going to introduce specifically the one sample z-test for testing a proportion P. There are other hypothesis tests that we will cover in this unit. In fact, by the end of the unit, we will have covered 8 different hypothesis tests. And besides those 8 tests, there are lots of others as well, right? So we're really only going to scratch the surface here on hypothesis testing. One thing that I want to point out to you right off the bat is that because we're going to be building up the procedures one step at a time, the way that we do each step might not be as streamlined as it will be when we're just running the process all the way through from beginning to end. And consequently, what I would tell you is that if you're trying to follow along with an example to work out a homework problem or something, you should skip to the last page where we're working out examples 5 and 6. Okay, because that's on those 2 examples, we'll go through the whole process from beginning to end. Okay, but in the meantime, what we're going to do is just kind of talk about the logic behind why we do the steps that we do, right? And we're going to build up that logic one step at a time. So with that in mind, the very first place to start, of course, is to talk about the null and alternative hypotheses in a hypothesis test. Okay, so in a hypothesis test, basically what we do is we pit 2 statements against one another, the null hypothesis and the alternative hypothesis. The null hypothesis, the symbol for the null hypothesis is this symbol right here, H sub 0, but I'll usually read that H null. And H null is what we consider to be the status quo. It's what's assumed to be true until we have evidence otherwise. Okay, and so consequently, the null hypothesis is going to be a statement that indicates that there's no change, no difference, no effect. Things are the same as they always have been, right? The alternative hypothesis is going to be denoted by this symbol here, H sub A. Some people denote it with an H sub 1, but in these notes, I'll use H sub A for the alternative hypothesis. And the alternative is usually a statement that the researcher is trying to find evidence to support. And it's definitely going to be a statement that indicates some kind of change or difference or effect. When running a hypothesis test, we can run them two-tailed, left-tailed, or right-tailed. And what that means is, notice that in each case, the null hypothesis is the same, right? The null hypothesis is always that whatever parameter you're testing, whether it's a proportion or a mean, the null hypothesis is going to be that parameter equals some value, okay? However, in a two-tailed test, the alternative hypothesis is that the parameter you're testing does not equal that value from the null hypothesis, right? That it's no longer equal to that value. That would be a two-tailed test. In a left-tailed test, the alternative is that the parameter is less than the value. And in a right-tailed test, the alternative is that the parameter is greater than the value. So I know that that's all very abstract and it might be a little confusing, but I promise if we look at a couple examples, it'll become more clear. So let's do that. Let's look at a couple examples. Actually, these are going to be the same examples that we led with, right? And we're asked to determine the null and alternative hypothesis, state whether the test is two-tailed, left-tailed, or right-tailed. So in part A, we have that scenario of the FDA wanting to know if the percentage of children who take the new antibiotic will experience headaches more than 2% of the time, right? Well, the null hypothesis is that no, they're not, right? The null hypothesis is that no, they're going to experience the same proportion of headaches as they would for any other antibiotic, right? P equals 0.02. And by the way, yes, I am stating the percentage as a decimal, okay? That's what we'll do when we're hypothesis testing. So null hypothesis P equals 0.02. The alternative hypothesis is the statement that the researcher is trying to build up evidence to support. In this case, the researcher wants to know if the percentage is more than 2%, right? The FDA wants to know if the percentage is more than 2%. This would be a right-tailed test. We know that it's right-tailed because in the alternative hypothesis, our inequality is pointing to the right. So it's a right-tailed test. Part B. A fast food fanatic wants to know if the accuracy rate at her local Chick-fil-A is different from the national accuracy rate of 96.4%. Okay. So she wants to know if the accuracy rate is different from 96.4%. Well, the null hypothesis would say, no, it's not different. It's the same, right? It's the same, right? The null hypothesis would be that P equals 96.4%. And again, I'm stating that as a decimal. The alternative here is that P is different from 96.4%. So the problem doesn't say specifically that she wants to know if it's bigger than that or less than that. It just says she wants to know if it's different from that. So we'll say not equal to 0.964. And because we're using a not equals in the alternative hypothesis, that makes this a two-tailed test. Okay, last one. Go ahead and pause the video and see if you can do part C on your own. Here's my solution. So part C says, suppose 83% of people say they like unicorn giggles, but you think that that percentage would decrease if they had to watch My Little Pony. Okay. Well, the null hypothesis would be that no, there's not going to be a decrease, right? The percentage is going to be the same as it always is, right? 83% of people are going to say they like unicorn giggles. The alternative hypothesis is that, yes, it actually is going to change, right? That P is, specifically that it's going to decrease, right? So P is going to be less than 0.83. And because we're using a less than symbol in the alternative hypothesis, that makes this a left-tailed test. Okay, so that's how we set up our hypotheses to run our test. And we're going to pit the null and alternative hypothesis against each other, and we're going to try to see which one of those hypotheses best explains the data, right? That's essentially what we're doing with hypothesis testing. So then the next question is, okay, so then how do we weigh the evidence, right, to decide whether or not we should stick with the null hypothesis? And to answer that question, we will usually compute something called the p-value. So the p-value of a hypothesis test is the probability that we collect a random sample that yields the sample statistic that we obtained, or something more extreme than that, assuming that the null hypothesis is true. Now, again, I know that that's a lot of words, and it's hard to capture the meaning of that right off the bat. So let me say it in a slightly different way. In order to compute the p-value, what we do is we begin by assuming that the null hypothesis is true. Okay, and then operating under that assumption, we compute the probability of obtaining whatever sample statistic we obtained in our study. Okay, now if it turns out that we end up with a really small probability, then that tells us we were probably wrong to make this assumption, right? And so probably it should be rejected. So a small p-value means we should reject the null hypothesis. Okay, I want you to memorize this definition. Okay, and more importantly, I want you to understand what the definition is saying. I'll ask you questions that test your knowledge of the p-value on problem sets and on tests. Okay, so I really want you to understand this. So make sure that you understand that definition. This chart is an attempt to write down in math symbols how we would compute the p-value. And, I think for a right-tailed test and a left-tailed test, it's actually not too bad. We've seen probabilities like this before, okay? For a two-tailed test, it's a little bit more complicated. So I'm also going to show you kind of a shortcut that we can use in Art of Stat to get p-values. But this right here, this bullet point right here is the key takeaway, right? And I said it a second ago, but let me just reiterate. If the p-value is small, then it's probably wrong to assume that the null hypothesis is true, and so we reject it. Okay, so a small p-value means we should reject the null hypothesis. Okay, because the only assumption we made when we were computing the p-value was that the null hypothesis is true. And so if we're getting a small p-value, if we're getting something unusual, then that means it was probably wrong to make that assumption, and so we should reject it. Okay, I think I've said that enough times. Let's look at a couple examples. Number 2 here says, restate the hypotheses from the scenarios in example 1, and then compute the p-values. Use art of stat to verify your results. Okay, well, we'll do it the long way in part A, and then I'll show you how to use art of stat, and then in parts B and C, we'll just use art of stat to do this. But for part A, well, first of all, it says to restate the hypotheses, so let's do that. It says, these are the same set of examples, by the way, that we've been working on, but it says a random sample of 300 children were given Medco's new antibiotic. 7 of them experienced a headache. A researcher from the FDA wants to know if we conclude that more than 2% of children experience headache as a side effect. Well, the null hypothesis, once again, is that no, there's no difference, right? P equals 2%. The alternative hypothesis is that, yes, actually P is greater than 2%. And by the way, what sample evidence do we have here? Well, the sample proportion is that out of our 300 children, 7 of them experienced a headache, right? 7 out of 300 experienced a headache. If you punch that into your calculator, that comes out to about 0.023. So yeah, the percentage here is a little bit elevated compared to the null hypothesis, right? 2.3% instead of just 2%. But is that enough of a difference, right, for us to really say that more than 2% of children experience headache, or is this just maybe random chance, right? Well, only one way to find that out, and that is to compute the probability of obtaining this sample result. Okay, so let's do it. So the p-value is the probability of obtaining that sample result. Or something more extreme, okay? So we're not just going to leave it an equal sign, because if 2.3% is extreme, then anything bigger than 2.3% would also be extreme, because this is a right-tailed test. So we'll actually compute the probability that p hat is greater than or equal to 0.023. When we go to compute this probability, we're going to be doing so under the assumption, right? So given that the null hypothesis is true, and the null hypothesis in this case says that p equals 2%. So you have experience computing these kinds of probabilities, right? We talked about this in chapter 2. We didn't always state them this way because we didn't always give the condition over here, but the condition was always implied. The way that you are used to seeing these without the condition is like this. And so you know that, hey, if I want to compute a probability involving p hat, I should use the normal distribution, right? Because p hat is normally distributed. So I'm going to go over to Desmos and use the normal distribution to compute this probability. Now, when I use the normal distribution, I have to enter something for the mean. And in the case where I'm trying to compute a probability involving a sample proportion, the mean I want to use is mu sub p hat, which we learned in chapter 2 is equal to p. We're assuming that we're assuming that the null hypothesis is true, right? So we're assuming here that p equals 0.02. So that's what we'll put in for the mean. And for the standard deviation, we'll use sigma sub p hat, right? Which is the square root of pq over n. And once again, we're assuming that the null hypothesis is true. So p would be 0.02. Now, if p is 0.02, then q is 0.98, okay? Remember, q is always 1 minus p. And then we have to divide by n, our sample size, which we said a second ago was 300. Okay, so that's the setup. And then to compute the probability, we're just going to type in probability p hat is greater than or equal to, rather than using the decimal, I'm just going to use the fraction, the exact value, right? So I'm going to say 7 out of 300. And let's see what we get. Okay, normal dist. 0.02 is the mean. Standard deviation is 0.02 times 0.98 divided by, I forgot the sample size. What is the sample size? 300. 300. Okay, I can zoom in on that. And then we want to compute the probability that x is greater than or equal to 7 out of 300. So that comes out to 0.34. Or if you want to go to more decimal places than just 2, you could click on the little down arrow. So we usually go to 4 decimal places with p-values. So we'll say 0.3400. Okay, and that's how we would compute the p-value. Let me show you how to do that same thing in Art of Stat, okay? So in Art of Stat, let's go to artofstat.com, and we'll go to Web Apps. And you have to scroll down, it's a little ways down, but you want to come all the way down here to confidence intervals and significance tests for one sample. And we want to run an inference on a proportion, okay? So don't go all the way down here to the 2 groups or further down. We're going to stick here with the one sample inference. And we want to do inference for a proportion. Okay. Now, I don't want to do an example from the textbook. I have my own example. We'll go to number of successes. That gives you a place to put in the sample size and the number of successes and all of that good stuff. So, so in our case, our sample size was 300. And we had 7 headaches, right, out of the 300 in our sample size. Now, I don't want to construct a confidence interval. We'll talk about doing that a little bit later in this section, or not in this section, rather, but in this unit. But I don't want to do a confidence interval right now. I just want to do a hypothesis test. They call that a significance test in the app. So we'll go to significance test. Under here where it says null value, that's the value in the null hypothesis, right? So in the null hypothesis, we said p equals 0.02. So 0.02 is our null value. And then finally, for the alternative, notice that it's running this as a 2-tailed test. You can see the alternative hypothesis right here. It's running that as a 2-tailed test, and that's because it's set up to run a 2-sided alternative. That's not what we wanted. We wanted to compute we wanted to know if p was greater than 0.02. Okay, so now this is the correct thing, and sure enough, right, we get the same p-value, 0.3400. Okay. Now, I know it took a long time for me to explain all of that, but that's just because this is our first time doing it. In reality, this is a much easier and quicker way to get the p-value than to do all of that work in Desmos that we were doing earlier. So this is the way that we'll compute p-values from now on, right? So p-value is 0.3400. Before we move on to part B, let me just comment on that a little bit, because remember, the whole reason we're computing this p-value is we want to know if the result that we obtained here is unusual under the null hypothesis, okay? And what we're discovering is that, well, we're getting a pretty large probability. It's not unusual, right? It would not be unusual for this to happen if the null hypothesis were true. And therefore, we don't have any reason to suspect that the null hypothesis might be false. And so we're not going to reject it, okay? Remember, small p-value means reject the null hypothesis. And in this case, we don't have a small p-value. We have a fairly large p-value, so we're not going to reject the null, most likely. But we'll talk about making our decisions a little bit later. Let's look at part B. It says, according to QSR Magazine, Chick-fil-A fills their drive-thru orders with 96.4% accuracy. A curious fast food fanatic wonders if the accuracy is different at her local Chick-fil-A, so she collects information from the store manager about the drive-thru accuracy of the local Chick-fil-A. In 350 orders, it was found that 326 were accurate. So just rewriting our null and alternative hypotheses, right? The null hypothesis is that The accuracy rate at this local Chick-fil-A is the same as it is everywhere else, right? P equals 0.964. The alternative is that the accuracy rate is a little bit different, right? She wonders if the accuracy rate is different. So P not equal to 0.964. What sample evidence does she have? Well, out of the 350 orders that she collected, 326 of them were accurate, right? So 326 out of 350. That's her sample evidence. And if you type that into your calculator, that comes out to about 0.931. Okay. So that is, a little bit of a difference there for sure. About a 3%, a little over a 3% difference. So, okay, now is that enough of a difference for us to definitely conclude that this local Chick-fil-A is less accurate? Well, there's only one way to know that, and that is to compute the p-value. Now, to compute the p-value this time, I'm just going to use art of stat. And here's how I would like for you to show your work when you're using art of stat. What I want you to do is just write down what app you're using in art of stat. In this case, the app we're using is inference for a proportion. Okay, so if you write that down, that'll let me know, okay, they're using art of stat, they're using this app. And that's important because we'll talk about different apps later, and sometimes you might get confused. And so it's good for me to see your work so that I can award you partial credit in case you get the wrong answer, right? Excuse me. So we'll use the inference for a proportion app. Now, the other thing that I want you to write down is write down whatever you feed in to art of stat, right? So one of the things you'll need to feed in is the null value, but we've already written that down here, so you don't need to write it down again. But one thing that you do need to write down is the sample size, okay? You'll be asked for the sample size. Sample size in this case is 350, so write down n equals 350. You'll also need to enter in the number of successes, x, right? So write down x equals 326, right? That's the number of successes. And then if you do that, art of stat will spit out a p-value for us. So let's see what we get. And I want to do my own example. We had a sample size of 350, and there were 326 successes. I don't want a confidence interval. I want to run a significance test. The null value, I think it was 96.3? No, 96.4. Okay, 96.4 or 0.964, right? 0.964. And this time we did want a two-sided alternative, right? We wanted to test the hypothesis that p was not equal to 0.964. And so there it is, right? There's our p-value, 0.0011. So p-value, maybe I should say is approximately, right? 0.0011. Okay. Last one. I'll let you do this one. Go ahead and pause the video, see if you can work it out on your own. Okay, here's my solution. So a recent poll found 83% of people say they like unicorn giggles. We tested 150 participants and made them watch My Little Pony first. And only 116 of them said they liked unicorn giggles. So does that represent a significant decrease? Well, the null hypothesis would be no. No, it's the same, right? Same. P equals 0.83. The alternative is that, yes, there was a decrease, right? There was a significant decrease. And what evidence do we have to say that there was really a significant decrease? Well, out of the 150 people, 116 of them said they liked unicorn giggles, and 116 out of 150 is only about 0.773. Okay, so this time there's almost a 6% decrease, right? A 6% decrease. So it seems like, probably that would be somewhat unusual, but there's only one way to know, and that is to actually compute the p-value. So to compute the p-value, we're going to go to you don't have to write down art of stat, but we're going to go to art of stat, and we're going to use the inference. By the way, if you want to abbreviate some of this, that's okay too. For example, you could just write inference for a proportion, right? And that would be good enough. N was 150, X was 116, and everything else that we need to write down is already accounted for here, right? So let's go to art of stat. So sample size was 150, number of successes was 116, I believe. Let me double check. Yeah, 150, 116. And we want to test p equals 0.83 against p less than 0.83. So p equals 0.83 against p less than 0.83. Double check your alternative hypothesis to make sure it's going the right way. And then you've got your p-value here, 0.0323. Alrighty. So we've discussed the fact that, hey, if you've got a small p-value, then that means it's probably wrong to assume that the null hypothesis is true. And so we should reject it, right? Small p-value means reject the null hypothesis. But that leads to an obvious question, which is, well, how small is small enough, right? How small exactly does the p-value need to be in order for us to reject the null? Now, in the past, we would always use 0.05 as our cutoff value for what we would consider unusual. But in fact, we could use any cutoff value that we want. And that cutoff value is called the level of significance, okay? And it's denoted by the Greek letter alpha, okay? The level of significance is going to be chosen by the researcher before they ever even collect any data, right? So in our case, the level of significance is just going to be given to us. And we'll talk about the level of significance in a little bit more detail at the end of the chapter. But for now, as I said, the level of significance alpha will just be given to us. And the most common values are 0.01, 0.05, and 0.10. And in fact, of those three, 0.05 is the most commonly used one. And that's why it's been sort of our default. But technically alpha could be anything the researcher wants, okay? So we'll discuss a little bit more about what that means later, okay? But the key takeaway is this. If our p-value is less than alpha, then we reject the null hypothesis, okay? That's how we make our decision. Technically, we would also reject the null hypothesis if the p-value equaled alpha. So if p-value is less than or equal to alpha, we reject the null. But it's so rare that you're going to end up with a p-value that's exactly equal to alpha that we can just kind of simplify things and say, if the p-value is less than alpha, we reject the null. Okay. On the other hand, if the p-value is greater than alpha, then we do not reject the null. But I'm usually going to write this a little bit different. What I'm going to say is if the p-value is not less than alpha, right? So if the p-value is less than alpha, then we do reject the null. If the p-value is not less than alpha, then we do not reject the null. Okay, I know that that's a little bit confusing at first, but you'll see why I kind of prefer to do that. And it'll become second nature to you. I promise it'll become second nature to you. A couple things I want to say real quick before we get into a couple examples. Our decision is always either to reject the null hypothesis or not to reject the null hypothesis. We're never deciding to accept anything, right? We don't accept the null, we don't accept the alternative, and we're also never deciding anything about the alternative, okay? We either reject the null or we do not reject the null. And at first glance, you might say, well, wait a second though, if we decide not to reject the null, isn't that the same thing as accepting the null? But the answer is no, it's not the same thing. Think about it like a criminal trial, right? When a criminal or when a defendant is on trial, they might get acquitted. That means they might get they might get to go free, right? They might be acquitted of their crime. That doesn't mean that the defendant is innocent, though. It just means that there wasn't enough evidence to convict them. There wasn't sufficient evidence to convict them. And so in a similar way, if we decide not to reject the null hypothesis, that doesn't mean that we accept the null hypothesis. It just means there wasn't sufficient evidence to reject the null hypothesis, right? So we're very careful and we're very precise about the language that we use in hypothesis testing, okay? All right, with that in mind, let's look at a few examples. Should we reject H null for the scenarios in example 2 if we use a level of significance of 0.05? What if we use alpha equals 0.01? Okay. So I think it would be helpful to rewrite the hypotheses again. For the Medco example, the null hypothesis was that P equals 0.02. I got to be careful with these equal signs. Equals 0.02. The alternative hypothesis was that P was greater than 0.02. And then we went ahead and computed the p-value for that, and we got a p-value of 0.3400. I believe that's what it was. Let's double check. Yes, 0.3400. So now the question is, well, should we reject the null hypothesis if we use a significance level of 0.05, right? So at alpha equals 0.05 level of significance, what we would do is compare our p-value to alpha. And what we're trying to decide is our p-value less than alpha? And the answer in this case is no. So I put a slash mark through it, right? The p-value is not less than alpha. So do not reject H null. Okay, that's at the 0.05 level of significance. What about at the 0.01 level of significance? Well, if we didn't reject at the 0.05 level of significance, we're also not going to reject at the 0.01 level of significance, right? Because it's still not going to be the case. 0.34 is not less than 0.01. So do not reject. Okay, so it looks like in part A, for the Medco example, it doesn't matter what level of significance you use, you're not going to reject the null. Okay, what about for the Chick-fil-A example? In the Chick-fil-A example, let me remind myself, Chick-fil-A example, yeah, we wanted to test P equals 0.964. We got a p-value of 0.0011. Okay, so the null hypothesis was P equals 0.964, and it was a two-tailed test. Whoop. 964, and our p-value was 0.0011. Double checking. Yeah, 0.0011. Okay, should we reject the null? Well, at the alpha equals 0.05 level of significance, again, we would compare our p-value to alpha. And what we want to know is our p-value less than alpha? And in this case, yes, it is, right? Our p-value is less than alpha. So we reject H null. Okay, what about the 0.01 level of significance? Would we reject the null in that case? Well, we compare our p-value to alpha, and we ask ourselves, is our p-value less than alpha? And once again, the answer is yes, right? So we reject H null. All right. Go ahead and give the video a pause and see if you can make a decision for part C. Okay, here's my solution. This one is, I think we get a different result depending on the level of significance that we use. But for the My Little Pony example, P was 0.83, and our p-value is 0.0323. Okay. So then let's talk about our decisions, right? If we use a 0.05 level of significance, then we would compare our p-value to alpha, and we would ask ourselves, okay, is our p-value less than alpha? And the answer in this case is yes, right? Our p-value is less than alpha, so we reject H null. But notice that if we use a 0.01 level of significance, then when we compare our p-value to alpha, in this case, our p-value is not less than alpha. Okay, so in this case, we do not reject. We do not reject H null. Okay, so this is how we make our decision, right? We compute our p-value, and then we compare that p-value to alpha. If the p-value is less than alpha, we reject the null. If the p-value is not less than alpha, we do not reject the null. The last step in a hypothesis test is to write out a conclusion. The conclusion is a statement about what your decision means for the alternative hypothesis, right? So again, the decision is about the null hypothesis, whether or not to reject the null hypothesis. The conclusion tells us what that means for the alternative, okay? So when we're giving our conclusion, we need to write out a complete sentence that addresses the original claim, okay? And not just in vague terms. It needs to refer specifically to the claim in the problem, okay? For example, if our decision is to reject H null, then our conclusion should say something like, there is sufficient evidence to indicate that, and then you should restate the alternative hypothesis in words, okay? If our decision is to not reject the null, then our conclusion should say something like, there is not sufficient evidence to indicate that, and then restate the alternative hypothesis in words. So again, notice that those negatives go together, right? Those negations go together. I'll emphasize that in a little bit more detail here in a second. But number 4 says to write a conclusion for each of the following scenarios. In part A, we had the Medco example, and we're asked to use a 0.05 level of significance. So at the 0.05 level of significance in the Medco example, we had decided to not reject the null hypothesis. So we do not reject the null hypothesis. That means, so we're not going to reject this hypothesis, right? So that means there's not sufficient evidence to support the alternative. There's not sufficient evidence to say that the proportion of children who experience a headache in the Medco group is more than 2%, right? There's not sufficient evidence to conclude that more than 2% of Medco patients experience headache as a side effect. Not Medco patients, but maybe Medco users, right? The antibiotic, whatever, experience headache as a side effect. Anyway, do your best to be as accurate as possible, but don't get too crazy with it. But I'll change this to users. Okay, so there's not sufficient evidence to conclude that more than 2% of Medco users experience headache as a side effect. Think about the scenario that we started with, right? When we first started looking at that example, we said, well, 2.3% of them experience headache. That's more than 2%, right? But apparently it's not a significant difference, right? It's not a significant enough difference for us to conclude that more than 2% of Medco users experience headache as a side effect. Okay, part B, Chick-fil-A example using 0.05. So for Chick-fil-A at the 0.05 level of significance, we decided that we would reject the null hypothesis, okay? So here we're saying, okay, we are going to reject this hypothesis. That means that there is sufficient evidence to support the alternative, right? There's sufficient evidence to say that the accuracy rate at this local Chick-fil-A is different from the accuracy rate of the national average, I guess. Okay, so there is sufficient evidence to conclude that the accuracy rate at this local Chick-fil-A is different from the national accuracy rate. Okay. So with that in mind, I'll let you give the video a pause and see if you can write out a conclusion for part C. Okay, here's my solution. For the My Little Pony example, at the 0.05 level of significance, we had decided to reject the null hypothesis. Okay, so we're going to reject the null in favor of the alternative. There is sufficient evidence, right, to say that people are less enthusiastic about unicorn giggles if they have to watch My Little Pony first. Okay. I'm just going to abbreviate and call it UG for unicorn giggles. Okay, but there's sufficient evidence to conclude that people are less likely to like unicorn giggles if they have to watch My Little Pony first. Okay, so that kind of concludes the steps for hypothesis testing. Here's a summary of what we've discussed, right? So if we want to run a one sample hypothesis test, the first step is going to be to write down the null and alternative hypotheses, okay? And then step 2 is to gather the sample evidence. In this case, if we're testing a proportion, then our sample evidence is p hat, okay? Step 3 is to compute the p-value. To test a proportion, we're going to use the inference for a proportion app from Art of Stat to get the p-value. Step 4, use the p-value to make a decision, right? If the p-value is less than alpha, we reject the null. If the p-value is not less than alpha, we do not reject the null. And then finally, step 5, write a conclusion about what your decision means for the alternative, right? If we reject the null, then there is sufficient evidence to support the alternative, right? Because we've rejected the null. So that means the alternative must be true. If we do not reject the null, then that means there's not sufficient evidence to support the alternative because we haven't rejected the null, okay? So let me run you through 2 examples from beginning to end. Okay, this one says, according to the Centers for Disease Control and Prevention, 19.6% of children aged 6 to 11 years are overweight. A school nurse thinks that the percentage of 6 to 11-year-olds who are overweight is higher in her school district. In a random sample of 65 6 to 11-year-olds in her school district, 19 of them are overweight. At the 0.05 level of significance, is there evidence to conclude that the percentage of 6 to 11-year-olds who are overweight is higher in her school district? Okay, lots of words there, okay? So it's maybe useful to give the video a pause, absorb the information, right, and really think about it. But let's go ahead and run through the steps of the hypothesis testing procedure. Step 1 is to state the hypotheses. The null hypothesis is that there's no difference between this nurse's school district and everyone else, right? 19.6% of the children in her school district are overweight. So P equals 0.196. The alternative hypothesis is the statement that the nurse is going to try to build a case for, right? So in her case, she thinks that the percentage of overweight students is higher in her school district. So she thinks that P is greater than 0.196. Okay, so that's step one. Now, step two is to get the sample evidence. What does our sample evidence say? Well, our sample evidence in this case would be the sample proportion. In her sample of 65 children, 19 of them were overweight. So that would be 19 out of 65. And if you punch 19 out of 65 into your calculator, that comes out to about 0.292. Okay, so there's almost like a 10% difference there, right? Now, on the one hand, that seems like, oh, that's a major difference. We're definitely gonna get a small p-value here. But on the other hand, our sample size was pretty small. So maybe we don't have great evidence after all. Only one way to know, right? And that's to go ahead and run the test. We're gonna use the inference for a proportion app in Art of Stat. And we're going to have to enter the sample size and the number of successes, right, in order to get the p-value. So let's go ahead and do that. Okay, so I want to do my own example. We had a sample size of 65 children. 19 of them were overweight. I don't want a confidence interval, I want to run a significance test. The null hypothesis said that p equals 0.196, and we wanted to know if the proportion is actually bigger than that, so greater than that. And so we can check our alternative hypothesis here. That looks good. And so we get a p-value of 0.0252. Okay, now we can use that p-value to make a decision, right? The way that we do that is we compare the p-value to our level of significance alpha, right? So let's make our decision. We compare our p-value to our level of significance, right? Alpha equals 0.05. And what we want to know is the p-value less than alpha? And the answer is yes in this case, right? 0.0252 is less than 0.05. So we reject H null. And then we can write out a conclusion. Since we're rejecting the null, that means there's evidence to support the alternative, right? So we would say there is sufficient evidence to conclude that more than 19.6% of children are overweight in this nurse's school district. Okay, and so that's how a hypothesis test goes, right? One thing that I want to kind of hone in on is this p-value. It's very important to me that you understand that that number is not just magic, right? This is the probability that we would obtain this result if the null hypothesis were true. Okay, so there's just over a 2.5% chance that we would observe something as extreme as this if only 19.6% of children were overweight. Well, that's not a very likely outcome, right? And so it makes us think, probably we should reject this assumption in favor of the alternative. And so that's exactly why we're concluding that, yes, there is sufficient evidence to say that the proportion is more than 19.6%. Okay? So one more. Go ahead and give the video a pause and see if you can run this one from beginning to end. Use what we just did in example 5 as a template, right? And see if you can run this hypothesis test. Okay, here's my solution. It says in 1994, 52% of parents of children in high school felt it was a serious problem that high school students were not being taught enough math and science. A recent survey found that 397 of 800 parents of children in high school felt this way. Are parents less likely to be concerned about the level of math and science education today than they were in 1994? Use alpha equals 0.05. Okay, null hypothesis is that no, parents feel the same way today that they did in 1994, right? So p equals 0.52. The alternative hypothesis, let me write it because I'm going to run out of space otherwise. The alternative hypothesis, we're asked, are parents less likely to be concerned, right? So is the proportion of parents who are concerned less than 0.52? Okay, so that's step 1. Step 2 is collect the sample evidence. Well, our sample proportion was 397 out of 800, which comes out to about 0.496. So, like a 2.5% drop. Is that significant? Well, maybe, maybe not. We did have a very large sample size here, so let's see. Only one way to find out. We've got to get the p-value, right? So we'll use the inference for a proportion. We'll put in a sample size of 800 and 397 successes. And we'll see what p-value we get. So let's head over to Art of Stat. Okay, so it's 800 parents, 397 of them were concerned. We want to run a significance test with a null value of 52%, right? The hypothesis test we wanted to run was p equals 0.52 against p less than 0.52. And it looks like the p-value there is 0.0894. 0.0894. Okay, we can use that to come to a decision now. Right? We do that by comparing our p-value to alpha. Our p-value 0.0894, and alpha in this case is once again 0.05. And we want to know, is 0.0894 less than 0.05? And the answer, of course, is no, it's not, right? Our p-value is not less than alpha in this case. So do not reject the null hypothesis. Okay, since we're not rejecting the null hypothesis, that means we don't really have evidence, sufficient evidence to support the alternative, right? There is not sufficient evidence to conclude that, and now we're just going to basically try to copy and paste whatever the alternative hypothesis was. In this case, you can almost always just copy and paste it from the question, right? Are parents less likely to be concerned about the level of math and science education? Well, no, there's not sufficient evidence to conclude that parents are less concerned about the level of math and science education. Right? There's not sufficient evidence to conclude that they're less concerned about the level of math and science education today than in 1994. Okay. Again, just to emphasize a couple things, right? So our p-value here shows that there's almost a 9% chance, right? An 8.94% chance. So almost a 9% chance that we would obtain this result if the null hypothesis were true. Well, a 9% chance is not that small. And so we really don't have good evidence to reject the null hypothesis. We don't have good evidence to reject this assumption. So we don't, right? We don't reject it, which means there's really not sufficient evidence to support the alternative. Now, I want to be very clear. I'm not saying that there's no evidence to support the alternative. I'm just saying it's not sufficient, right? There is some evidence, right? There's some evidence to support the alternative. Our sample proportion was smaller than 52%. So there's some evidence, but it's not sufficient, right? There's not sufficient evidence to conclude that parents are less likely to be concerned. Now, the other thing that I want to point out is notice how all of the positive statements in our decision and conclusion go together, right? The p-value is less than 0.05. So we do reject the null hypothesis, and therefore there is sufficient evidence, right? All of those positive statements go together. Whereas all of the negations also go together, right? The p-value was not less than 0.05. So we do not reject the null hypothesis, which means there's not sufficient evidence. It is always this way with hypothesis testing. There's never any mixing and matching. Okay, all of the positive statements go together and all of the negative statements go together. There's never a case where you'll decide not to reject the null hypothesis, but then turn around and say that there is sufficient evidence to support the alternative, right? You will never mix and match like that. All of the positive statements go together, all of the negative statements go together. Now, there's much more that we could talk about with like the logic of all of this, but if I give you too much at once, it's not going to do any good. So we will come back, and this entire unit is about hypothesis testing. So if this feels like overwhelming and super confusing to you, that's understandable, but I promise you that by the time we get to the end of this chapter, it's going to be second nature, because you will have run so many examples of this, you could do it in your sleep. Okay, so in the meantime, just practice. Use these, especially 5 and 6. Use examples 5 and 6 as a template for how to attack a hypothesis test, and you're going to do just fine. You'll get the hang of it before you know it. So that'll do it for now, and I'll check in with you again in the next section.